Okay, so we are going to cover a new chapter that's functional dependency and normalization. Let's quickly review what we did so you know why we learn things like this. So we start with requirement analysis, and we produce an ER diagram. And from ER diagram, we can map to the relational model, right? So there's a mapping here. So after we produce a relational model, we be able to use SQL to create our database and specify queries. And that's what we did. This is a complete sequence of creating database from scratch, right? Starting from the very first thing requirement, analysis until at the end, you'll be able to create a database, insert tuples and query the database and give your customer, give your client the result they want. So we learned the methodology to do this, and also, you should be able to apply this to different application. You will take the senior project course when you're near to graduation, and for that, most of the teams, many teams using database in the back end. So the whole thing can be quite useful there and to build something successfully. Okay. And after we finish this chapter is considered as more like a theoretical analysis about the given design. So if you'll be able to analyze the requirement correctly, produce the ER correctly, okay, be able to use the mapping rule correctly to relational model, then, so this is your design eventually, this is the implementation, this is like a coding part, right? And so your design should be already in certain normal form. And of course, you don't know what that means, but that's a certain normal form considered as good quality already. However, not everyone have everything done correctly. And maybe people doing things differently, maybe misunderstanding, maybe they don't know the right methodology to handle things. So you may, for example, you go to work and you may have somebody, the database they designed like 10 years ago, and the people ask you, so how is the design, right? So what is the design, good or bad, things like that. So in database field, at least after you finish my class, the way to evaluate a database design is not simply a word of good or bad. You want to using something called the normal forms. And so you evaluate them to say they are in third normal form, or they are in second normal form, or they are in both called normal form. So you see terms like this, and then the other side should know what kind of quality is the design. So the quality of design can be evaluated using normal forms. It also, so basically in 134 class, we're going to learn how to use normal form to evaluate existing design. So the outcome of this is eventually when I gave you a schema, and then I ask you which normal form, you'll be able to answer me, say, this is the second normal form. That's the outcome of this learning outcome of this chapter. Okay, so let's see what is this piece. So already talk about, what is the design, right? So design basically, since we did the formal training, right? We know this is our way to do the design correctly. And basically think about design is like grouping of attributes to have one table, another table. So for the same requirements, some people may say, I'm going to grouping this type of attributes together, and I produce 3 tables. And the other one may say, I produce 10 tables, right? So they can have different design. And the question is, what are good design? Okay, how can you evaluate them? And so when we evaluate them, we use formal measures, and that's called the normal forms. And in order to do normal forms, we have to start something called a functional dependency. And so I'm going to show you after we finish that. Okay, after we finish that, we are going to code something called the normalization, and we're going to learn something called the normal forms. So that's the one I mentioned a few minutes ago. But in order to do this, we have to learn something called functional dependency first. This is the foundation. And this chapter, we have a lot of definitions. And so make sure you'll be able to follow me. Otherwise, you'll feel lost, after you miss, say 20 minutes or 30 minutes of content. So make sure you'll be able to follow. So what is a functional dependency? Functional dependency, they are constraints. They are derived from meanings and interrelationship of the data attributes. So this is the one coming from the meaning. Where can we get the meaning? We get meaning from user requirements, right? So everything is based on user requirements. So user requirement give us the meaning of two attributes, and we can derive those informations and to know how do they relate it. And of course, some of them like common sense, like for example, social security number, right? So we know social security number is unique for every single person in the United States. And so when we know a social security number, guaranteed that's related to only one person, right? Things like that. So, but they are also coming from requirements, right? So they just like not explicitly say like this. Okay, so functional dependency is the property and it's of the semantic meaning, right? So again, emphasize coming from the meaning. So what is a functional dependency? For functional dependency, we're going to, so this is totally new, we're going to introduce functional dependency like this, from X to Y. So there are two sets of attributes. So X is a set of attributes. Y is another set of attributes. So say X can have social security number, employee name, things like that. So they are basically attribute, right? Attribute can be one attribute, can be more than one, a set of attribute. And they are subset of R. R is the whole relation. When we analyze this at this point, okay, we already know the company database. We already divided them into tables, right? So now let's just get rid of the table concept right now for just temporarily pretend that we don't see tables. We only see attributes. Say when I have the company database requirements, I see many attributes. And now I try to analyze the relationship between different attributes. So how, for example, the address of an employee related to their social security number, things like that, right? So I have the R basically means all the attributes I have, right? And we have this one. So we have the functional dependency is a constraint. And when we have tuples, whenever we have any relation state, okay, it doesn't matter when, just any relation state, we have the following constraint. Okay, so see if we have a tuple, so I have attributes X, Y is coming from R, and R has many attributes, and then I have tuples, right? So because attributes values, attribute value, I have one tuple, another tuple. And then for any two tuple, T1, say T2, like this, doesn't matter which one, any two, we have the following condition: if T1x equal to T2x, and remember this notation in the relational model chapter, that's mean what are the value corresponding to T1. So here, so T1x has the corresponding attributes. So T1x is whatever value corresponding to that x part. T2x is whatever value corresponding to that, right? So like a 1, 1, 1, 1, draw, and 1, 1, 1, 1, something like that. So we have that. So whenever we have T1x equal to T2x, means this particular one equals to this particular one, then they must also have, so if this is true, then we also need to get the y part, right? So y also have attributes. This also need to be the same. So whenever they are the same, this must be the same. Right? This is true for any two tuple, any relation state. And if this is the case, we say there's a functional dependency from x to y. X is a set of attributes, y is another set of attributes. So I'm going to give you some examples and can help to understand what this one means. So I know this is totally different from what we covered so far. Okay, we are not actually using the things like an ER diagram, those things. We are just analyze the attribute itself to see how do they related. Okay, so let's see some example here. So we can see, okay, so x to y, okay, x is a function determines a set of attribute y if the value of x determines a unique value of y, right? So this is basically what I mean. The unique value of x determines the unique value of y, right? Okay, so example here. So we can see social security number functionally determine employee name. Okay, so this one, say, I have a requirements, right? When they're writing, they say social security number is unique in United States, and every single person have only one social security number, and any social security number can only relate to one person, blah blah, things like that, right? So then we know social security number function determine employee name. So if we think about a relation with SSN and ename, they are two attributes within my relation. Okay, it doesn't matter what are other attributes. So I just say I have SSN, I have ename here. And I'm going to select a state. And doesn't matter which state, what time you take the state. And I'm going to select any two tuple, and doesn't matter which one you select. So when you select two tuples, if we see the same social security number, we definitely know they are exactly the same ename. So if this is true, then we say we have functional dependency, right? Functional dependency from SSN to ename. This is a definition of functional dependency. The unique value of X, that's SSN, determine the unique value of ename. Okay. Okay, and I'm going to give you more on that, on the more examples. Okay, let's see. So I have X to Y, and I have a functional dependency from X to Y. So that's one way to say it. I have functional dependency from X to Y, and Y is functionally dependent on X, and X is the left-hand side, Y is the right-hand side of the functional dependency. They are just basic terms that we're going to use. So sometimes I say, what is right-hand side? You know what I mean is this one, right? Okay, so this is the one repeating what we have. X, Y holds, if whenever two tuples have the same value for X, then they must have the same value for Y. Okay, so a functional dependency is a property of the relation schema R, not the particular relation state, because we need to make sure this is true on any relation state. Not only just like say today, 6 o'clock, this is true. It's not sufficient. Every single state need to be true. So that's actually a property belong to the schema. So that's basically here, right? So it's a constraint on all the instance, relation instant at any state. Okay, so more example for functional dependency. So we'll see this a lot. So another way to say employee name is functionally dependent on SSN, right? Okay, so this one, say employee name is functionally dependent on social security number. Here, project number, right? So project number on the left-hand side determines the project name and location. So in this case, if we know a project number, we guarantee can identify one and only one project name and only one location. So this one give you an example that right-hand side can be more than one attribute. Two attributes here. So when we have the same project number, I have the same project name and same project location. The next one is a little bit hard, to understand compared to previous one. So employee SSN and project number together, okay, so when something on the left-hand side, if we have two attributes or more, okay, this is what means the combination of SSN and project number determines the things on the right-hand side, that's the hours, okay. So when we know the unique combination of SSN and the project number, I know there's only 1 hours associated with that. Say, for example, employee 111 on project number 1 working on 3 hours. And this is, once you know this combination, you only have 3 hours. So it's not possible, you have this and you have another 2 hours possible. You could have like the other employee on number 1 working like 2 hours. So this is the one dependent on the combination of two of them. Okay, all right, so that's one example functional dependency. I totally understand this chapter is harder to understand than the others. So let's see, I try to slow down whenever, when you feel I need to slow down. Okay, so let's see. When we have a set of functional dependency, and basically we get a set of functional dependency from requirements, right? And can we infer additional functional dependency or not? So this is a basic question mark. If I have a set of functional dependency and I have another functional dependency, I want to know, can I infer additional functional dependency like this from the existing one? This is coming from requirement, for example. Or should I always go back to the requirement, redo everything, and to see if this one can be covered or not? And so the answer is we can do inference. So for example, if I have a set of functional dependency, like this one, this is the one, say, when I read the requirement, I found out I have the following functional dependency here. And my question here is this true? Is this true? Is this true? Do we have those functional dependencies? So in other words, ename and bdate are they functionally dependent on SSN bdate combination or not? How do we know they are true or not. And how do we know? The way to know it is we can use something called inference rules. So those inference rules allow us to know for a given set of functional dependency, once we have the given set, we can use the inference rules to know whether they are true or not, okay? Whether we have those functional dependency or not. Okay, and we have totally 6 inference rules. The first 3, they are the basic rules, and 4, 5, 6, they can be deduced from 1 to 3. Okay, so you need to remember not only 1 to 3, but 4 and 5. The number 6 you can always easily deduce. So, and it's kind of long to remember, but 4 and 5, they are very frequently used and really simple. And I will show you, you'll be able to remember at this right moment after I finish talking about that. So let me talk about each of the rule and give you some example to help you to understand what the rule about. So notation, just simplify things. When I say X day, it means X, the set of attributes of X and the set of attributes of Z together. So X can be a set of attributes, Z can be a set of attributes. XZ basically means we mingle all the attributes together into one set. Okay, so so X is, for example, X has A and B 2 attributes, and Z has C and D attributes, and this part is actually A, B, and C, D. Okay, and I'm going to just using this to simplify rather than say X comma Z. Okay, all right, so let's see this one. So this is the one talk about reflexive. What this one means is if Y, so this is the right-hand set, if it is a subset of X, X is the left-hand set, this functional dependency always true. So you always have this functional dependency. And if I give you an example, you will see why this is true. The example cannot prove this is true, but it can help you to understand. So when I have, for example, SSN and e-name, so this is employee name, social security number on the left-hand side, and the right-hand side is the social security number. So let's see a functional dependency like this. Okay, so this is the Y part, and this is the X part. So now you can easily see Y is a subset of X, right? So Y is a subset of X, and since this is true, then this is, so okay, Y is subset of X, this functional dependency is always true. You always have this functional dependency. And let me show something that, so I have tuples here, for example, and say I have SSN here, and if I have 2 tuple with same SSN, with the same e-name, right? And the other side is also SSN, so this is the one. Of course, if this the same, this is the same, they are the same, right? So according to functional dependency definition, when the same left always get to the same right, and this is always true. So that's why this is always true. Okay. Okay, so let's go to the second one. The second one talk about if I have x to y, if I know this is true, if I put the same thing on both sides, remember they are side, right? So on both sides, I have one set, another set. If I put the same thing on both, say if this is the z element, then whatever produced still true. Say x, y is true, then this is always true. Let me give you an example here. Say I have SSN to E name. So suppose this is the functional dependency I can produce from the user requirements, right? SSN to E name. And if I add something on both sides, so social security number and address, and I add e-name and address on here also. So that is adding. Okay, so I have SSN address to e-name and address, right? Okay, so that's this one, and this is this one. So I just want to show you if this is true, then this is true. So if I have many tuples, go back to the definition. If I pick any two tuples, okay, so this is SSN field. So if SSN and SSN, they are the same, for example, according to the first rule, right? Then the e-name must be the same, right? So that's this one tell me this is true. I want to add address on both sides. So address, if I have address, doesn't matter what is the address, right? So if I have SSN address together, and since this part is also address and they are the same, so you actually compare the same thing on this side and this side. So that's why this is always true according to the definition. One is using this, the other one is using this part. Okay, so this particular rule tell you, okay, in order to be true, that means the same SSN, same address, then this part must be the same, right? So whenever you have the same, using the same functional dependency, you already know they are the same. And this is the same thing, right? So they are the same already in this side. So when you consider this part on the right-hand side, they are the same. So they are, according to the functional dependency definition, this functional dependency hold. This is true. Okay, so let me, I know this is a little bit confusing. Let me explain this one more time. Okay, so for this is the given, right? This part is given. So we know for any two tuples, if we have the same SSN, then must have the same e-name here, right? So that's for this one. Then if we go to the second one, this is this part. I try to show you using this example to show when this is true, this is also true, okay? So in order for this particular one to be true, we need to require that no matter any two tuple you selected, when we have the same SSN, okay, the same address, then this part need to be the same. And let's see that the same or not. The e-name part, the e-name part is the same because this one tell me same and then must be the same. And the address part, this actually cross the two part, right? Both on the left and on the right. So we already know on the left side, if they are the same, then on the right side, they are the exactly same thing, right? So that's why they are the same. So same SSN, and the same address will guarantee you have the same e-name and same address. Okay. So how that, and so this is the one. Let me get rid of this. So the next one I want to do is number 3. So this one I have x to y and y to z. Then I have x to z. So simply, so for example, I have 3 tuples here, right? 4 have. So if I pick any two tuple, okay, I have x and y, z, and each of them can be many attributes together. So let me simplify, see if they are just one attribute. So if x the same, same x, right? And we know from here, if I have the same x, I'm going to have the same y, right? So same x get the same y. Whenever I pick 2 tuples, if I have the same x, they guarantee have the same y. And then if we using this one, if we use this one, I know since I have this functional dependency, if I have the same y, then I'm going to get the same z value. So what we can see here is the same x value always get the same z value. It's just because when you use x to determine y and you get the same y, and for the same y you define z, you get the same z. And so this one, whenever they are the same, then this z must be the same. According to the definition, if whenever you have the same x, you have the same z, then I have a functional dependency x to z. Okay. Okay, very frequently used. Number 3, okay, we use this all the time. Okay, let's move on. So now let's move on to number 4 and 5. So you can see they are opposite to each other. Decomposition is if you have x to y, z, then you have x to y and x to z. This is the one really commonly used. And so let me show you one. So if I know social security number determines name and address. Okay, so this is on this part. Then I know the following things are true. That's SSN2 name must be true, and SSN2 address must be true. Okay, so if I have a couple of tuples here, if I pick any 2 tuple, okay, and according to this, I know if we have the same social security number, right? So I'm going to do this. I guarantee to have the same name, right? Also, I guarantee to have the same address. So that's according to this one. Same here, then same here, and same here. And then when we go to this part, so if we know this is true, we can, using this inference rule to know this is true, this is true. So if we have this functional dependency, we also have this functional dependency and this functional dependency. And you see this is this, whenever they are the same, then name must be the same. Okay. Remember, according to the definition, whenever they are the same, then means we have this functional dependency. This functional dependency is true. And then if we have the same SSN, we have the same address, means this functional dependency also is there. So that's for this one. And the union is the opposite of that. The if part is here, and then we'll try to get this one, right? So say if this is the fact, we know this is true, this is true. from given set, like from user requirement, we found out this is true. And then we know using this inference rules, this is also true. Okay, let me try to use the same one. So SSN to ename. So if we have the same SSN, we are going to have the same ename, right? So that's this one, tell me. And let's see this one. So we have SSN to address. SSN to address, right? Same SSN, same address. And so that's what this one tell me. And when we combine two of them, you will see whenever we have the SSN, we're going to have same ename. This one tell me we're going to have the same address. This one tell me. So that means this is true. Same SSN, same ename, and same address. So that's this union rule. So I don't think it's anything significant to remember. Like IR1 is, the IR3 is transitive. The name doesn't matter. You just need to see whenever you have this, you'll be able to apply them. So some of the case, later we'll see when you see things, you need to use them to say, I need to actually, when I see this, I need to have this kind of format. So you can use this rule to directly break into two. So now let's see the last one. So this is the one you don't need to memorize. Whenever you use it, you can directly deduce from the existing one. Let's see how to do that for fun. Okay. Okay, so let's see. This part has this, so x to y, and this is given. Okay, so what I'm going to do is I'm going to put a here. So I'm going to put a wx to wy here. So I know this is true because, so I put the same thing on both sides, right? So that's actually coming from IR2, right? So IR2 tell you if I have this is true, then this one is true, right? Here, so you may curious say it's after, it doesn't matter, that's a set of attributes. A set has no order, right? You can mingle, you can change the values, different orders. So, say ABC in a set is the same as BCA, right? So put before or after doesn't matter. So I have that, and then this is also given. This is also given, right? That's this part. And so we know the if part, I want to see the then part is true. So what I need to do is taking this one, this is deduced by R2, this is given. And from that, if we see IR3, okay, so that's the one, right? So X, Y, Y to Z, then X to Z. So from IR3, this one to here, here, exactly same, right? X, WX to this and to that, and then eventually we can produce. And that's this one. So that's why where's the 6 coming from? Using the existing one, you'll be able to produce this one, deduce from, actually I use the 2 and 3 only. I'll be able to produce this one. Okay, so we'll do more next class.